welcome back to my channel. Today we're going to look at transition metal complexes. We'll first look at definitions and then we'll have a look at their formulae and naming. First of all, what is a transition metal complex? This is a compound which is made up of a transition metal ion which is bonded covalently to ligands. So what is a ligand? A ligand is a molecule or a negatively charged ion which has an electron pair available to datively covalent bond to the transition metal ion within the complex. Ligands can be classified according to how many atoms they use to bond to the transition metal ion. For example, a monodentate ligand, which means one tooth, bonds through one atom. A bidentate ligand would bond through two atoms, and a hexadentate ligand would bond through 6. An example of a hexadentate ligand would be EDTA. Coordination number is the number of bonds that the transition metal in the complex forms. A dative covalent bond is a covalent bond in which both electrons that are shared come from the one atom. Here we have 3 examples of complexes. We're going to have a look at the coordination number and classification of the ligands. In this first example, the metal coordination number can be seen as 6. This is the number of bonds which are coming from the metal. The ligand classification can be seen by counting how many atoms the ligand is using to bond to the metal. There is only one ligand present here. All of the atoms are joined together. Each of the green dots shows an atom which is being used to bond to the metal. This is an example of a hexadentate ligand, as 6 atoms are used. In this next example, the metal coordination number is 4. We're counting the number of bonds coming from the metal. If we look at each of the ligands, we can see that each ligand is only using one atom to bond to the metal. This means that each ligand is a monodentate ligand. In the final example, again we are counting the number of bonds from the metal to give us the coordination number. There are 6 bonds from the metal. This gives a coordination number of 6. There are 3 ligands attached to this metal. Each of the ligands is using 2 atoms to bond to the metal. This means that each ligand is a bidentate ligand. Look at each of these complexes. State the coordination number of the metal and for each ligand give its classification. Pause the video now. For this first complex, to find the coordination number of the metal, you need to count how many lines are coming from the metal. There are 6 lines. This means the metal coordination number is 6. For the ligand classification, you need to look at how many atoms each ligand is using to bond to the metal. There are 3 ligands and each of the ligands is using a nitrogen and a carbon atom to bond. This means this is a bidentate ligand. In the second example, again for metal coordination, you count how many lines there are from the transition metal. In this case, there are 6. This is the most common coordination number that you will deal with. For each of the ligands, you need to count how many atoms are being used. For the 2 ligands on either side, they are both using 2 phosphorus atoms. These are bidentate ligands. For the hydrogen atoms, they are using 1 atom to bond to the transition metal, so are monodentate ligands. There are a number of different ligands that you need to learn. You must know the ligand formula and the ligand name. The first type of ligand is for the halogens, for example, chloride. A chloride ligand would be called chlorido. A fluoride ligand would be called fluorido. A bromide ligand would be bromido. An iodide ligand would be iodido. For oxygen, the ligand name is oxido. For water, the ligand is called aqua. And for an ammonia ligand, the name is amine. Spelling is important here, there are two M's. For a cyanide ligand, the name is cyanido. For a hydroxide ligand, the name is hydroxido. For an oxalate ligand, which is a bidentate ligand, the name is oxalato. And finally, a carbon monoxide ligand is carbonyl. You need to know which ligands are neutral and which have charge. We're now going to have a look at the naming rules. These are the rules that we will use to name the transition metal complexes. The first rule is that the positive ion, the cation, should always be named before the negative ion, the anion. You've been doing this for years in chemistry. For example, sodium chloride. The positive ion is sodium, the negative ion is chloride. So we always have sodium and then chloride, or Na plus, Cl minus. When naming the complex part, you need to name the ligands first alphabetically before the metal ion. Where you've got multiple of the same ligands, then we would use the prefixes di and tri that we would have used in organic chemistry previously. If the complex is overall negatively charged, then the name of the metal needs to end in ate. The Latin name is used for some metals, for example, cuprate for copper and ferrate for iron. Finally, the charge of the transition metal is always shown as a Roman numeral after the transition metal name. Let's have a look at an example. The first step is to calculate the charge of the complex. We'll then use this to help us calculate the oxidation state of the transition metal before finally looking at naming the complex. So, calculating the charge of the complex. To do this, we have a look at the counter ions. We have two chloride counter ions, each with a charge of -1. The ligands, water, are neutral and therefore have no charge. So the overall charge of the complex is 2+. When naming the transition metal complexes, the positive ion always comes before the negative ion. This is also the case when writing the formulae. So looking at this complex, we can see that the part in square brackets is positive, so will be named before the second part. The first thing we need to name is the ligands, and these have to be named alphabetically before the transition metal. So the ligands here are water ligands, and therefore are called aqua. We have 6 water ligands, so we need to put in the prefix hexa to tell us how many there are. So the start of the name is hexa aqua. We then follow with the transition metal itself, and because the part in square brackets is positive, we can leave this as copper. Immediately after the transition metal name, we put in the oxidation state in Roman numerals 2, and then we can follow with the negative ion, which is chloride. Here are some examples for you to try. The steps will remain on the screen. Pause the video now. So in this first example, the first thing we need to do is calculate the charge of the complex. We do this by looking at the charge of the other ions. So we have 2 fluoride ions, so that is 2-. The overall charge of the complex is 2+. Using the rules that we've previously learned on calculating oxidation states, we can work out the oxidation number of the cobalt. As the ligands are neutral, then they have a charge of 0, which means that overall the oxidation number for cobalt is 2, and we can use this as a Roman numeral later. So the positive part of this complex is the part in square brackets, which is the bit that we're going to name first, and we need to name the ligands first. So the ligands here are amine ligands, and there are 6 of them. So the name has to start hexaamine, and spelling is very important here. You must have 2 M's. The part in square brackets is positive, so we can continue with the name as normal, so cobalt, and then Roman numerals 2 for the oxidation number. We're then going to finish the name with the negative ion, which is fluoride. The second example is slightly more complex. We'll start in the same way. We're going to calculate the charge of the complex. So we have 2 positive ions for potassium, which means that the part in square brackets is worth 2 negative. We need to keep this in mind for when we are naming this later on. Using this information and the rules that we know, we can calculate the oxidation number of the iron. Overall, the part in square brackets is 2 minus. The Fe will have a positive charge of some variety. We have water ligands, which are neutral, and 4 cyanide ligands, each with a charge of -1. This means if we rearrange this algebraically, then the iron has a charge of 2+. All metal ions must be positively charged, even if the part in square brackets is negative overall. So now, naming the positive ion first, we are naming the part on the left-hand side, potassium. We can now look at the part in square brackets, the complex ion, and we're naming the ligands first. We need to name them in alphabetical order, so it's best to sketch these out at the start. So we have aqua ligands and we have cyanido ligands. So they've been put into the formula in alphabetical order. We have 2 aqua ligands, so it's diaqua, and we have 4 cyanido ligands, tetracyanido. Because this is a negatively charged transition metal complex, we need to make sure that we have the proper name for the metal, which will be ferrate. We're then going to put the charge of the metal afterwards, 2 as Roman numerals. Overall, the name is potassium diaqua tetracyanido ferrate 2. In this example, we have a cobalt complex with 1 chloride ligand as our negative ion. Overall, the complex has a charge of 1+, and we have 2 ligands, 1 neutral and 1 with a negative charge. We have 2 of them, so overall that is a charge of -2. If we rearrange this, then we find that the cobalt has an oxidation number of +3. We can use this later for our Roman numerals. Naming the positive part first, we are looking at the complex ion. We have 2 different ligands, so they need to be named alphabetically. We have amine ligands and chlorido ligands. There are 4 amine ligands, so we need to put on the prefix tetra. So we have tetra amine, and then we have 2 chlorido ligands, dichlorido. Overall, the complex ion is positively charged, so then we can just put in cobalt with the transition metal oxidation number 3 as a Roman numeral, followed by the negative ion, chloride. So as we've done before, we're going to start by calculating the charge of the complex. We have a 2+ ion here in front of the complex, meaning that the complex is overall 2- charged. We can then use the rules to work out the oxidation number of platinum. The carbonyl ligands are neutral, and the oxalato ligands each have a charge of 2-. If we rearrange this algebraically, then we can find that the platinum has a charge of 2+. When naming this compound, we will name this with the positive ion first. Positive ion here is magnesium. Now looking at the complex ion, we need to name the ligands first. We have 2 ligands present, the first being carbonyl, and we have 2 of those, and the second being oxalato. Again, we have 2 of those. So naming them alphabetically, we have dicarbonyl, dioxalato, and then the whole part in square brackets is negative. This means we need to change the end of the transition metal name to ATE. So this will become platinate. We then put the oxidation number in Roman numerals in brackets afterwards, so 2. So here's our final example. So first of all, we're going to calculate the charge on the complex. So we have 3 nitrate ions, each of which have a -1 charge. So overall the complex has a charge of 3 positive. Using the oxidation state rules, we can calculate the oxidation state of chromium. All of the ligands are neutral here, so chromium has an oxidation state of 3 positive. The complex ion is the positive ion here, so will be named first. We have 2 ligands present, amine and aqua. Please be careful with spelling. There are 5 amine ligands, so we have pentaamine, and only 1 aqua, so just 1 aqua after the pentaamine. As it's positive, we can then just put in the transition metal name chromium, followed by the oxidation number 3, and then finally the counter ion nitrate. Let's look now at turning names into formulae. The steps that we follow are to have the metal first, followed by the ligands separated with brackets if needed. You add the square brackets around the complex part and then calculate the charge of the ion, showing this on the outside if you're only dealing with the ion. If there are counter ions named, then you can use the charge of the complex to work out how many are needed. So here the metal we are dealing with is chromium, so we can put down the symbol for chromium, Cr. We then have to look at the ligands. We have 2 ligands in this case, the first being amine and the second being aqua. For amine we only have 1, and it is NH3. For aqua, that is water, we have tetra, which is 4. So we're going to put brackets around the H2O and put a 4 on the outside. We then add square brackets around the whole of the complex, and then we can calculate the charge. The Roman numerals tell you the oxidation state of the transition metal, in this case 2, and the ligands that we have are both neutral. This means that overall the charge of the complex is 2. Here are some examples for you to try. Pause the video now. So in this example, we are looking at a complex ion. So we're going to look at steps 1 to 4. So first of all, we're going to look for the metal, and it is cuprate. So that is copper. The ATE ending will give us a clue for the charge overall at the end. We have 2 ligands present, amine and chlorido. So the first ligand, amine, is NH3, and we have 1 of them. And the second ligand is chlorido, Cl, and we have 5. We're then going to put square brackets around the whole ion. We can now use the charges present to work out the charge of the complex overall. The copper is a 2+ ion, and each of the chlorines are 1-. This gives an overall charge of -3. From the AT ending, we can see that this should be a negatively charged complex. In this next example, we do have counter ions present. We're going to start first with the transition metal from the complex, which here is mercurate for mercury, which is Hg. We only have 1 ligand present, the Untitled Ligand, and we have 4 of them. We put square brackets around the complex, and then we need to calculate the charge of the complex. We have 2+ for the mercury, and each of the Untitled ligands will be 1-, so that's 4- overall. The complex is a negatively charged complex of 2-, which means that we require 2 silver ions which have a charge of 1 positive each to be able to balance this out. Here's another example where we have a counter ion. We're going to start with the cobalt, CO, and we have 2 ligands present. We have an amine ligand and a chlorido ligand. We have 5 amine ligands, so we need to use brackets around the NH3. We put 5 on the outside. We have 1 chlorido ligand, Cl, and then we can put square brackets around the whole of the complex. We can then go about calculating the charge of the complex. We have 3 positive for the cobalt and 1 negative for the chlorine. The amines are neutral. Overall, this leaves us 2 positive. We have sulfate ions present and they are 2 minus, so we only require 1 sulfate. For this example, we have another negatively charged complex. Here we have ferrate, which is iron. We have 2 ligands present, aqua and cyanidal. We have 2 aqua ligands, so we need to put brackets around the H2O and put the 2 on the outside. We have 4 cyanidal ligands, so again brackets are required with the 4 on the outside. Square brackets will then go around the full complex before we calculate the oxidation number. We have 3 plus for the iron, aqua is neutral, and 1 minus for the cyanidal, so overall 4 minus. This gives a 1 minus charge for the complex ion. This means that we need 1 potassium ion to balance the charge. This last example is our most complex example. This one is an ion on its own. We have chromium as the transition metal, and we have 3 ligands, carbonyl, fluorido, and hydroxidal. We have 2 of each of the ligands. Carbonyl ligands are CO ligands, and we require brackets around them. Fluorido ligands is an F, and we have 2 of them, and then hydroxidal is OH, and again we have 2 of them. We then put square brackets around the whole complex and calculate the charge. We have a chromium 6 ion, neutral carbonyl ligands. We have 1 minus for each of the fluorides and 1 minus for each of the hydroxides. This gives an overall charge of 2 positive for the ion. Match each term to its definition. Pause the video now and give this a try. So the first term that we have is for complex, and a complex forms when ligands bond to a transition metal ion through dative covalent bonds. Our second term is a ligand. A ligand is an atom or molecule with a negative charge or lone pair that it can use to form a dative covalent bond. A dative covalent bond is a covalent bond in which both of the shared electrons are from one atom. The coordination number is how many bonds a transition metal has made, and bidentate is a type of ligand which bonds through 2 atoms. Thank you for watching my video. I hope that you found it helpful. Please remember to subscribe and follow me on Twitter at Miss Adams Chem and Instagram Miss Adams Chemistry for regular updates on new videos and flashcards every day. Bye for now.